All right, so we can see that there is this change of arrival times, which we can then convert to effectively an orbit. And so when you do this for all of the data, as best as you can, you realize that there's not just 2 planets, there's actually 3. Because these pulsars are amazing how accurately you can measure things.
And you can measure, for example, the masses of these things. The innermost one is actually smaller than the moon. Tiny.
So 2/100ths of the Earth in its mass. That is tiny.
The other 2 are a bit further out, and they are both about 4 times the mass of the Earth. So there's nothing like that in our own solar system. These are big, but they're not as big as the gas giant planets, but definitely bigger than any of the rocky planets.
But when you say far out, you don't really mean far out. I mean, this one is 2/10 much closer than Mercury is to the Sun, and even these 2 are about, or as I said, you know, they're sort of in where Mercury would be. So they're all very close to the star itself.
And we can also measure the eccentricity. This is a measure of how off-circular the orbit is. Eccentricity of 0 means the orbit is a perfect circle. Eccentricity of 1 would mean it's a parabola. And these things are actually pretty close to 0. We can't really measure it for the innermost one, so we're assuming it's 0. But for these 2, where we can measure it, the eccentricities are very, very small. They're close in and in almost perfect circular orbits.
Right, and you don't expect planets to be born with nice circular orbits, especially after they've been slammed with a supernova or something.
Yeah, they could have been born. Some of the stars in our own, some of the planets in our own solar system have circular orbits, but after a supernova gone off, there certainly won't be any more. This is an artist's impression of what these things might look like. Not particularly accurate. In fact, from one of the planets, the other ones just look like dots. They wouldn't they'd be too far away to actually see the disks. And this is an artist's impression of what a pulsar might look like. You look at the very strong magnetic fields, but no one really knows that they're like that close up.
And they've even put aurora, meaning there must be some sort of atmosphere there, but I don't think I'd be going for a vacation at this planet.
And these are going to be cold, irradiated planets. They're going to be zapped by huge amounts of X-rays from the pulsar and not much heat. So these are going to be frigid, radioactive, probably very unpleasant places to live. I don't think a vacation there is going to be much fun.
Doesn't look nearly as nice as this picture says.
But then this is a puzzle. I mean, we've just agreed that this, around a neutron star, around a pulsar, is the one place where you cannot get planets, because we know that planets form when the solar system forms. But after that, to get to a pulsar, you've got to go through at least one supernova explosion. So that's puzzle number 1. How did the planets survive this immense explosion?
Yeah, and the other question is, why are their orbits so circular? Almost certainly they survived that supernova explosion. That's going to knock them into some eccentric orbit, and so something would have had to make them go into a nice circular orbit again, but the pulsar isn't going to do it. It's a long ways away.
And then we get a third puzzle. Remember, to form one of these millisecond pulsars, you need a companion star, which will swell up and dump gas into it, and will then leave behind either a neutron star or a white dwarf. But we're not seeing that. These planets are nothing like massive enough to do this. So where is the companion star that got the millisecond pulsar split up to these things? So let's look at some possible explanations for how you actually form these things.
Okay, Paul. So we have a bunch of problems here of why I didn't think there should be planets here in the first place. So how are we going to actually go through and come up with a scenario to explain why these things are here?
Well, let's talk through 3 of the theories that people have come up with that might possibly explain where these things come from. The first theory is they really are survivors. They were there before the star went supernova and somehow they survived. So let's see if this is at all feasible. I mean, the reason we like this idea is because we know that planets form at the same time as stars. Remember, a giant molecular cloud collapses, forms a spinning disk of gas, and planets form then. So that's when the planets should form. Can they possibly survive?
So we have a couple problems here. First of all, we know we need to have 2 stars in the center. And if you're going to have planets going around 2 stars, they got to be out a ways, or they're going to get ejected by these 2 stars.
Okay, so they're going to be much further out than the planets we actually see around the pulsar.
That's right. So that's the first problem. The second problem is these are big stars, and so as they run out of their hydrogen in their core and start burning helium and heavier elements and fusing it, they become huge. They become red giants or even red supergiants, and they're going to expand out to huge distances and, quite frankly, potentially engulf these these planets. And when those planets get engulfed in the red giant, they will get dragged and they will sort of get consumed by the star.
Yeah, the second star will also be in the middle, but that's got enough mass to keep it orbiting even inside the other star for the short period, but the planets probably don't.
That's right. So that's a pretty serious problem. And then that star explodes.
Okay, so let's calculate what happens, whether the planets actually survive the explosion of a star.